All right, I want to talk to you about your next homework, which is going to be using the GIS software to find the watershed. And so before we get started on that, let's backtrack a little bit and talk about DEMs. In an earlier assignment, you worked with DEMs, which stands for Digital Elevation Model. And you may recall that these are rasters. And so it's a surface, and it's made of equally sized cells. And in each cell contains a single numeric value. And in the DEMs, this numeric value indicates the elevation of that cell above sea level. And so that's why you can call it an elevation model. And we used these earlier because you can do things like calculating slope, aspect, so which direction the cell is facing, so you can tell like how much sunlight it gets, view shed, so at certain times of the day, what's going to be shadows and what's not going to be shadows, things like that. They're very common and they're very useful. And we could spend a lot of time talking about these because they've been around for a while, and now you can get some DEMs that are very precise, that use lasers and LiDAR to find the elevation at a very small scale. We could talk about that later. The basic idea of a DEM is all we need today. It's a raster of elevation above sea level. And so just to give you a quick example, here would be a very, very small DEM. And in this example, the cells would be 10 meters by 10 meters. And that's a fairly common size, although again, the newer ones made with LiDAR can be like a half meter by a half meter. Maybe even smaller than that. Within each cell, you see the number that that cell contains. And in a DEM, that's elevation above sea level. And in this example, that would be like meters above sea level. And so if you think about these as elevations, you can picture the topography of this particular piece of land. And so you can tell that the northwest is the high point, and the southeast is the low point. So you can already just in your mind picture the slope, right? And earlier we had the software calculate slope, and you can see how you can calculate slope. You can tell which areas are higher and which areas are lower. Now, one question that we can ask that's very important to ecology and to biologists, if it rains on this area, where would the water go? And so obviously, if the ground slopes down to the southeast, the water is all going to run toward the southeast. And how do you know that? Well, you know that water runs downhill, right? Intuitively, you can understand that. In real life, you're not going to have a small DEM like this, and you're not going to be able to see the numbers. Real DEMs are huge, and they've got thousands and thousands of cells. And so how are you going to tell where the water goes in that situation? It's not going to be a simple example like this. Well, that's where the software comes in. For every cell, you'll notice that, except for the ones that are right at the edge, but for most cells, they're surrounded by 8 other cells. And so for every cell, you can look at those 8 surrounding cells, and you can tell, is the water going to flow into this cell or out of this cell relative to the surrounding cells? So for example, let's look at this particular cell right here that's 85 meters above sea level. Excuse me. If it rains, any water that is in, for example, this cell, of course, some of that water is going to run into this cell here. Now, if you look at this cell that's 98 meters above sea level, of course, some of it's also going to run into this cell, and some of it's going to run into this cell, and some of it's going to run into this cell, and water from this cell is going to run into this cell, and so on, right? And again, intuitively, you understand that the greater the difference in numbers, the greater the slope, and the faster the water is going to run. And so there's lots of models built into the algorithm. And so this is something that would be more appropriate for a soils class, geology class. But for our purposes, you can understand that if you know the elevation of each cell, you can predict where the water is going to run out of that cell or into that cell. And if you do this for all the thousands and thousands of cells, that's how you can delineate a watershed, because you can tell where every drop of water is going to eventually end up. And that's what we're going to do today with the software. So a watershed is basically the area around a stream that drains into the stream. So if you have a stream and you've defined its watershed, that's the area where, theoretically, any raindrop that falls in that watershed could end up in that stream. And you can define this at many scales, right? You might be looking at a ditch and you can just look at the area that drains into a ditch. But that ditch might run into a small stream. So you might want to look at the watershed for that small stream. That small stream might go to a big river. You might want to define the watershed for that big river. So it depends upon the kind of question that you're trying to ask. That will help determine what scale you're going to look at. Here at Murray State, we have the Watershed Studies Institute, and they have a saying there, everything is a watershed. And that's something that you have to think about. Everything that happens on land in the watershed affects the water coming out of that watershed. Everything that gets dumped in the terrestrial area, everything that grows, all the soil, all the geology, everything that happens in a watershed eventually is going to affect the water coming out of that watershed. And of course, I don't need to convince you of the importance of clean water. And so that's why understanding watersheds is so important, and so important to really understanding streams and lakes and wetlands. And so consequently, delineating a watershed, it's an important GIS function, and that's why I would like for you to practice. If you know the watershed, you can answer such questions as, how much stuff will drain into the stream. If you've got a bigger watershed, then you've got more stuff, more things that can run off that watershed into the stream. What kinds of things will go into the stream? And so that is determined by what kinds of land use, for example. And so if you have a lot of agriculture or a lot of hard surfaces, then that's going to determine how much stuff and what kinds of stuff is going to get into that stream. That's going to affect the stream's water quality. You can ask questions about like how much erosion is expected to occur. How steep is the slope in the watershed, and what kinds of soil and what kinds of land use. That's all going to determine how much erosion you're going to have. There's all kinds of important questions that you can answer once you know the watershed of a stream. And so delineating a watershed in the software, it's a multi-step process. We of course start with a DEM. The first thing is just a small step. We're going to fill sinks. And so these are going to be little minor depressions, right? And so the software will, if we didn't do this, there'd be all these small areas where the software thinks the water's going to collect. But we're looking on a little bit bigger scale than that. So we want to fill these sinks, all these small little, puddles and things, because we're going to be looking at a larger scale. Once we do that, then the next step is to determine flow direction. And so that's essentially the same thing as determining slope. And so we're going to make a raster that's going to tell us which direction the water's going to flow from each cell. From that, then, the software can figure out where the water's going to collect. And ultimately, that's going to be the streams. So we're going to be able to make a stream map from the DEM. And in fact, that's how most stream maps are made, is you don't go out and travel down the stream with a GPS and take GPS points. You just use an elevation model and you can predict where the stream should be. Finally, there's a term called a pour point, and we're basically going to have a pour point, which is a point at the mouth of the stream through which all the watershed's water must flow. And so you can put that pour point sort of anywhere on a stream, and you'll determine the watershed everywhere upstream from that point. And so where you put this point kind of helps determine the size of your watershed. Okay, so for your homework, we're going to try and find the watershed around a local stream called the Bayou de Chêne, which is French for Dog River or Dog Creek. And this is here in western Kentucky, and there's a tributary on the Bayou de Chêne called Jackson Creek. And Jackson Creek is the only place in the world we find the endangered relic darter. And so it's this neat little fish, and it's found nowhere else except this small tributary, and maybe it's in the Bayou de Chêne. But it's an endangered species, and we need to protect it. And so one important thing that we need to do is to understand the watershed around the stream in which this fish lives. And so that's what we're going to be doing in homework 15. So what we're going to do is we're going to start with a DEM of the area around Bayou de Chêne. And so from here on in this video, I'll be cool, and I'm just going to call it the BDC. Anyway, by figuring out this watershed, like I said, this is an important use of the GIS software, but also this is going to be a good way to practice using QGIS. We're going to be using lots of different things in QGIS, and I want you to become comfortable with the software. So anyway, I'll walk you through this step by step, so follow along and let's get to work. Good girl, Rosie. Okay, as always, we start by making a new folder. And so I made this folder here for homework 15. And first thing we're going to do is here's the zip file I sent you. And this is the Bayou de Chêne digital elevation model. And so it's just a raster that I downloaded and I prepared for you. So we're going to extract that. And so now we've got this folder. If you look into it, you've got a TIFF file. And again, a TIFF file is a type of raster file, and it contains a coordinate reference system is coded into the TIFF file itself. So that's why TIFF files can be advantageous, because you don't need a whole lot of files. Like with a lot of other GIS data, you've got multiple files. Here we've got just one, and it's all we need. So awesome. So I'm going to go ahead and launch QGIS. And you might notice as I go along here that sometimes some of the processes take a while. I've got an older computer here at home. You know, obviously I'm working at home. I'm not working at my desk, and so this computer is a little slow, but it still runs it. And I'll try to kind of speed things up so you don't have to sit and wait on my old computer. Anyway, we got QGIS. We're going to start a new project here. Now, we always concern ourselves with the coordinate reference system, and you'll notice that this is going to start my project in the WGS 84. And that's a reference system that, again, is very common. It's basically the geographic coordinate system. It's latitude, longitude. It's commonly found in association with GPS data. And so it has the same shortcomings as the geographic coordinate system or latitude, longitude, in that, you know, it's difficult units, right? So we're going to change the coordinate reference system as soon as we get started. That's just the default, and you can change this default setting if you want to. And so before I do anything, I'm going to go over here to Project, go to Properties. I'm going to find the Coordinate Reference System tab, and you can see down here that it's currently set for the WGS 84, but I would rather change it to this UTM Zone 16 North, which is appropriate here for Western Kentucky. And if you look at the map, you see it runs through Western Kentucky. Again, what's the advantage of this? We're using a projection, so we're taking a you know, spherical Earth and we're making it on a flat map. So you can use simpler geometry. It works with meters instead of, like degrees. And so it's just easier. Of course, we'll have to distort the map a little bit, but on the scale we're working at, it doesn't really matter. EPSG 26916 is the code that we always like to use. And so, again, this is in my recently used coordinate reference system. I can come down here and I can scroll around for it. I can come up here and I can search for it. There are several ways that you can find this particular transformation or projection. And so I'm going to go ahead and hit apply and OK. And so now my project is based in that coordinate reference system. And that just makes things easier in the long run. It also seems to make the software run better. And especially when we're working with rasters, if we can keep everything in the same coordinate reference, you're going to be happier in the long run. Okay, so now that we've done that, I'm going to go ahead and I'm going to save the project just so I've got it saved. And so here's my homework 15 folder. So I'm going to call this homework 15 completed. And it's just a good habit to save as much as you can. That's all I'm going to say about that. So I'm going to come over here to the browser and look for my homework folder, which is going to be right here. And you can see here's that folder I created when I unzipped the zip file. So I'm going to open it. And here's that TIFF file. And so let's just drag it into the project. And there you go. And so you can kind of roughly tell that, where the streams are going to run. Again, I've gone ahead and clipped this down for the area around the Watershed, and the software is colored based upon the values in the cells, and the values in the cells are elevation. And so when you zoom way out, you get to see kind of a topographic map. So let's look over here at the layers, and you can see that for this raster file, it runs from 0 to 174. 0 is just for the very edges where I clipped this. There's no area here in Western Kentucky that's right at sea level. That's just an artifact of the clipping process. The highest point is 174 meters, right? And the wider areas are high ground and the dark areas are low ground. And you can see that the water is going to flow into these lower areas. And here's the Watershed, and it dumps into the Mississippi down here. And that's why a DEM works for delineating a watershed. We could do something like right-click on this and go to Properties. And we can go to Symbology. And we can play with the colors here. We might change this to single band pseudo color. And there's several different color ramps, but we can go, so this color ramp, red would be the low areas and blue would be the high areas. Let's invert that and apply it. And well, again, you don't see very much difference because these low values are just, again, artifacts at the end here. So I could play with that symbology a little bit, and maybe I could make the minimum, I imagine it probably doesn't get much lower than 100. And so let's classify, and if we apply that, and there. And so you can clearly see the highest areas are over here, probably near Mayfield, if I had to guess. And you can see the lower areas are the ditches and streams in the Mississippi River, just like you would expect. Awesome. I'm going to save, because I just like to save all the time. And again, I want you to think about what a raster is It's important to know the characteristics of your raster. Let's just pick an area, and I'm going to zoom in. And I'm going to keep zooming in. And if I zoom in far enough, you see what we're starting to pixelate. You're able to see each of the pixels of this image. And each of those pixels is one of these cells in the raster. I can zoom in a little bit more, and you can clearly see that we've got equally sized cells. That's what a raster is. And each of those cells contains a single value. So if I take my information button, or my identify button, and I click on a cell, you see that its value is 111.252. It's 111.25 meters above sea level. And if I click on the one next to it, it's 113 meters above sea level. And that's exactly what a DEM is. So it's important to know what value your elevations are in. And like I told you, these are in meters above sea level. It's also important to know the size of your cells. That just tells you what kind of precision you have, or resolution. And so you can go to the metadata and look for that. Another way to look for it would be to get your measure tool. And we've got the measure tool set to meters. And so I'm just going to measure the side of one of these cells. And so I'm going to measure this, and it's 8.7, my hand slipped, sorry, 8.854 meters. And so that's actually roughly 30 feet. And so this raster probably was originally 30 feet by 30 feet was a common pixel size for rasters. So my guess is that that's where this one came from. I can dig out the metadata and find it, but so we can say that the cell size is 8.854, give or take, and that's a good thing to know. All right, and so I'm going to right-click and zoom to layer so we can zoom back out. As always, I'm interested in knowing the coordinate reference system I'm using, so I'm going to right-click on this raster, go to Properties again. This time I'm going to go to Source, and you can see the coordinate reference system is EPSG 26916. So it's the same as my project. That's exactly what I want. And that's why I prepared this DEM for you, so that we can have a DEM that is in the proper coordinate system. All right, so now we're ready to start identifying our watershed. Okay, and I'm going to show you a few things as we go along that will be helpful in anytime you're going to be working with QGIS. And so this is the first thing. We're going to, we want to have like a base map. In ArcMap we had base maps, and it's kind of nice, and it just helps you to figure out where your map is, on the planet.
Okay, we'd like to get an idea of exactly where this DEM is and where these streams are. And so we can use a trick that we used earlier. We have these XYZ tiles that we have installed. And I've got a few of them here. I'm going to go ahead and just take Google Maps and drag it into my project. Go ahead and do the transformation. Drag it to the bottom. And I'm going to zoom out a little bit. And so you can see in general where the DEM lies here in western Kentucky. And so this, tells us we're in the right place. So I'm going to go ahead and zoom back to this layer. I don't need that Google Maps anymore. And there you go.
Okay, so there are a number of specialized tools that we're going to need to make this watershed. And as with anything with GIS, there's more than one way to skin a catfish. So I'm going to show you the way that I learned how and that works, but there may be other ways that this will work. So just be aware of that. The tools that we're going to need are found in another plugin. So we're going to go to plugins again and manage the plugins. And I want to search up here for process. And you get a bunch of stuff, but that's alphabetical, and you can find this processing plugin. And so this is a whole bunch of tools that we need. And so if this is not checked on yours, go ahead and install it. Mine's already installed, so I'm good. Once you have that plugin installed, you come over here to the processing menu and turn on the toolbox. And here are a whole bunch of tools that we can use in different situations. Okay, so recall our first step is to fill sinks. So within this DEM, there's going to be a lot of small areas that are shallow depressions. And if we don't fill those, then they'll each look like their own little watershed or their own little water collection area, and we don't want that. So I'm going to come over here to the processing toolbox, and I'm going to search for fill. And you can see that down here under Saga, which is a group of tools, there's several fill sinks. You'll also notice that it's up here in my recently used because I've recently used it. So once you use a couple of these tools, they'll start to show up at the top. And so there are several to choose from. We're going to use this one from Wang and Liu. And so we're going to double click it. So this tool has already chosen our Watershed DEM as the DEM it's going to work off of.
So I noticed in the newest version of QGIS, this minimum slope defaults to 0.1 degree, whereas here it's 0.01. You want this to be set to 0.01, so you will have to change the default if you're using a newer version of QGIS.
So the fill DEM is what we're going to create. We want to give that a name. So we're going to save it to a file. And we're going to choose our homework folder. And we're going to name this new raster filled. And you'll recall that after filling the sinks, we need to determine flow direction. Well, this tool will go ahead and do that. So it's going to create a raster, so we're going to give that raster a name. So we're going to save the file. And we'll call this flow direction. And it even looks like this tool will go ahead and calculate the watersheds for us as well. But we're going to use a different tool, a slightly different algorithm. So we're not going to put give this a name, and we're not going to check this box. You'll find with a lot of these tools that you have, again, more than one way to do it. So I encourage you to play with these and see which ones work better for you. At any rate, now we're ready to go, and we're going to run the tool. I will tell you this, realize that the tool has to look at every cell in this DEM and figure out, where the water is going to run, and then what to fill, and then which direction the water is going to flow. And so it does take a little bit of time to run. So if it's running and you're like, oh, I'm worried that it's hung up, just let it go for a little bit. Now, that was my experience. And again, I'm running a fairly slow computer. Yours may run a lot faster. At any rate, just relax and give it time, and hopefully it'll run all the way through. So let's do it. Let's hit run. Okay, if we close that, you'll see that we've got a couple of new rasters over here, our flow direction raster and our filled raster. and you can turn off flow direction, and the filled raster looks like a lot like our original DEM, and it should, because in general it's going to be the same DEM. There's only small areas around here that got filled, and so their values got changed a little bit so as to not make depressions. So this flow direction is interesting. You see that it's got runs from -1 to 7, and this is a special code that this kind of raster uses to delineate which way the water is going to flow. So let's take a look at that real quick. Okay, as I mentioned, each cell is surrounded by 8 other cells. So if you just took one, then you can see there's 3, 4, 5, 6, 7, 8 cells around it. And so the water can flow into one of 8 directions. Now it's a little bit more complicated than that, right? It might be able to flow into different ones. There's algorithms that determine ultimately which direction the water is going to flow. But that's why when we look at flow direction, it's split into 8 values. And so this can be called the D8 flow directions. And so here's your example showing how those numbers can translate into a direction. Now, in your map, the directions don't run from 1 to 8, they run from 0 to 7, but there's still 8 of them, right? Also, on our map, earlier I said there's 8, there's actually 9 classifications, because your map can also have -1. -1 indicates somewhere that's perfectly flat, or no flow, and that's going to be area where water collects. Okay, the next step is going to involve finding the Strahler order for the streams. So the software is going to be able to find where the streams should run, and then it's going to give them this Strahler order. And this is an idea that you run into a lot when you look at streams and rivers. Basically, you can just label any stream, any tributary with its Strahler order, its Strahler number, its stream order. They're all kind of the same thing. And the smaller headwater streams are given a number 1. And then whenever 2 streams with the same number come together, the resulting stream takes on the next highest number. And so as you go downstream, the stream order numbers get larger and larger. And this is a good way to organize streams. And the lower order streams, you know, the headwaters, the 1s and the 2s, are going to be very different, have different characteristics and different biota than the lower order streams. And so this is very commonly done, and there are several ways to do it. You could sit down with a map and you can kind of figure this out yourself, but the software has an algorithm, and we're going to use that, and it's going to figure out the Strahler order for us. Okay, so we're going to use a tool to find the Strahler order. So let's go to the processing toolbox and search for Strahler, and you see there's just a single tool that comes up. So I'm going to double click that, and we want this to work on our filled DEM. All right, so it's going to use the filled DEM, and we're going to create a new raster. So we're going to give it a name that we're going to call Strahler. And then we're going to let it run. Okay, so now we have this raster of Strahler order, and I want to make it look better so I can tell what's going on. So I'm going to change this to single band pseudo color again. It's got 1 to 10 values. Here I've got this spectral color ramp. I'm going to go ahead and go with this. So I'm going to hit apply and OK. And if I kind of zoom in on a spot, you can see the blue indicates, you know, a higher order stream. And so you can kind of see this blue, and that shows you where the stream is. So we've kind of delineated the stream, but it's not very clear, it's not very helpful, and that just indicates, you know, those cells that have, you know, the very highest order, but there are some, you can kind of see some tributaries here that are maybe a little bit lower order, but they're also part of the stream. Anyway, we want to recolor this so that we can better see the streams. And so I want to show you this because it's going to use a technique that we use a lot with rasters. You know, again, remember that rasters are surfaces of cells, and those cells have numbers. And so you can take and you can do math on those rasters. And we do this a lot. You did an earlier assignment where you sort of combined different rasters. We're going to do that with the raster calculator. So let's go up here to raster and a raster calculator. And all our rasters show up here, but we're working on the Strahler. And so we want to double click Strahler. And what we want is we want to know everywhere in this raster that has a value of 8 or greater. And so all those smaller order streams, all the red, we're going to get rid of all that. We just want the major streams. And so those are going to have the higher order. Now, 8 is a good number, but you can play with this if you know, and see how it affects the results. So we want Strahler, we want to go to greater than or equal to, and then 8. Oops, excuse me. And then I'm going to click down here and type 8. So if you look at my expression, that's what we're going to do. We're going to evaluate this. This is going to create a new raster, and it's what they call a Boolean raster, where it's going to be true or false, or 0 or 1. Everywhere, every cell in which this expression is true is going to have a 1 in my new raster, and everywhere else is going to have a 0. And so for the output layer, I'm going to give it a name. And so I'm going to find and make sure I'm still in my same folder. And this is going to be Strahler 2. And we'll just say that. And when I go ahead and hit OK, now I've got a new raster. And if you look over here, everywhere that's you know, where it was less than 8 is now black and is given a value of 0, and everywhere that was greater than 8 is white and is given a value of 1. So we've created a dichotomy here, either a 0 or 1, or a yes or a no. So let's see if we can't recolor this to make it look better. So we're going to go again to Properties and Symbology. We're going to change it to Single Band Pseudocolor again. There's only 2 values, 0 and 1. And so if we leave it like this, where red is 0 and 1 is blue, let's hit Apply. And if we go back and look at our raster, we can zoom in, and you can see that now we have these blue areas look a lot more like streams. It's still pretty garish with this red. Let's get rid of this red maybe. So let's click on that color, and you can see the opacity is set to 100. Well, let's set that opacity to 0. Let's make it completely transparent, which is the opposite of opaque. And when I hit Apply, so now what you're seeing is the raster, the original Strahler raster underneath. So let's turn that off. Let's turn off the flow direction. And so now we're looking at our Strahler raster on top of a DEM, and you can see it looks like streams. And you can see that if we sort of look based on our DEM where we expect streams to be, that's where these higher ordered streams are. So it seemed to work. And we could turn off all these rasters and turn on our Google map and zoom in, and you can compare the Google map Let's get rid of that. And so you can see where the Google map is showing streams, and that pretty much coincides with where we're showing streams. So it seemed to work. Pretty cool. Okay, now we're ready to find the watersheds. We're going to use a tool here called the Channel Network and Drainage Basins tool, which again is a Saga tool. And so, again, I'm going to choose my filled DEM to work on. Now, here's something I don't fully understand. We already ran the tool to get flow direction and Strahler order, but this tool also will calculate those. So I don't have an answer for this. You might be able to just use this tool only, so you can play with that. But again, I know what works, and so I'm going to go with this. My threshold, I'm going to set to 8 again, just like I did earlier when I was looking at the Strahler method. Flow direction, I don't need to do, I've already done it, so I'm going to leave this blank and I'm going to uncheck this box. Now something else I've noticed, it's very easy to get confused about which box goes with which raster, so just pay attention. But it looks like the box is under the name, so I'm leaving this blank and unchecking this one because I don't want flow direction. I don't want flow connectivity. I've already got Strahler order. Now, there's a couple of places where you can save the drainage basins. Again, I can't explain this. Just go with the flow. We're not going to use this first one. Now the channels we would like, and so this is just going to make a file that's going to sort of mimic that Strahler raster we made earlier. So let's give that a name. So we're going to save it to a file, and we're going to call it channel. And we're going to leave this box checked so we can see that one. And so this bottom one for drainage basins, we want to save this to a file. We want to call it basins. And we want that box checked. And this very last one, junctions, I don't think we want that. And so that should be everything we need. So let's hit run and see what happens. Okay, so that ran. So let's take a look. So if you look over here, we've got a couple somewhere. We've got a couple of new layers. We've got one for the channels and one for the basins. We're going to go ahead and recolor the basins. So let's go to symbology. Let's change this to categorized. And we're going to base it just simply on the ID value, because each one of those polygons is its own basin, its own watershed, and it's going to assign random colors, which is good. So let's classify, hit apply, and take a look. All right, and so then let's make these channels show up a little better. So let's change the symbology there. And let's maybe make it black. And let's make it a little bigger. And looky there, I'm going to go ahead and save my project. And so if you look, you can see that that algorithm calculated a watershed for all these different streams. So again, why did we bother calculating Strahler order and flow direction in that earlier? It's just nice to know, and it was just a good way to explain them. I think you might be able to just jump straight to this last tool and run it. Try it. If it doesn't work, you know that what I just did works. Okay. And so this is very good. Now again, if you look in the middle here, this is the BDC. This is the Bayou de Chêne. And if we zoom in a little bit, you can see it's got a little funny turn right here. And so it gets right to the edge of this watershed of this smaller one. There's probably some sort of a ridge or something that runs here, and so it turns funny, and then you've got some other tributaries that run in, and then eventually it runs into the Mississippi. So where exactly this watershed ends, does it end here? We probably, would say it ends at the Mississippi. At any rate, whoops. I'm all over the place. You can see how that tool worked. And just something else I want to show you. I also sent you a different zip file called jacksoncreek.zip. So I'm going to go ahead and extract it. And if I look, once I extract it, I should have a new folder called Jackson Creek. And inside this folder, and this is like, this is a shape file. So this is like we saw earlier, where you've got several files that all combine to make one GIS file. And so this just represents Jackson Creek, that area where the relic darter is most likely found. So I'm going to come back up here to the browser, and here's that Jackson Creek folder I just made, and here's that shape file. So I'm going to go ahead and drag it onto the map. And I'm going to go ahead and turn off this Strahler layer. And this Jackson Creek, you can't really see it, so let's go to Properties. And let's make it maybe bright intense red. And let's thicken it up again a little bit. And now you can see Jackson Creek. So you can see that's a pretty small stream. And it's way up in the upper end of Bayou de Chêne. It's a very low order stream. And so that is where this fish lives. So that's pretty cool. All right then. Okay, so we have a pretty good representation of the watershed around the Bayou de Chêne. But what about the watershed around Jackson Creek? Or what if there was anywhere else along this river that we wanted to find the watershed for? An upstream portion, or just a portion of this watershed. And so Jackson Creek is a good example. Since that's mostly where we find the relic darter, we'd like to see what's going on in the watershed just around this small creek. And so there's, again, probably many ways we could do this, but here's one way. We need to get a pour point, and we need to establish that pour point right where Jackson Creek enters the Bayou de Chêne. And so I'm going to kind of zoom in on that point a little bit. And so this red line, that's the shapefile that I gave you, and that's based from a different source. And so it's pretty close to what we've determined. But really, what you see here is we want to use the channels that we just determined, right? And so again, if you zoom in, this is that channels shapefile that we created, and that's the vector version. And we could go back to the Strawler 2, and you can see Strawler 2 shows the same channels, but it's a raster version. So you can see the cells here, right? And so we probably would be happier if we were on the raster version, since our calculations are in raster. Let's drag this channel up on top so it lays, so now we can see them both. So we need to choose a pour point that lies, somewhere right around here where Jackson Creek runs into the Watershed. And we're going to need those coordinates. So let's find a tool that's going to help us. I can hover the cursor right there, and down here at the bottom you can see the coordinates, and so I could just probably write those coordinates down, and therein, remember that we set the coordinate reference to UTMs, so that's in northing and easting in meters. But let's try a tool that's going to help us here. So let's go up to plugins. Let's go find a new plugin called Coordinate Capture. And so you see I have not installed it yet, or I haven't activated it. It's been installed when I installed GIS, and so I just need to check that box to activate it. Good deal. So when I hit close, you see I've got a new window down here. And so I can find coordinates using this window. And so for example, I can start capture, and I can find the spot I want and click on it, and there it gives me the coordinates, and it actually gives me the coordinates in decimal degrees and also in UTM, northing and easting, which is what I want. And so cool. So I'm going to copy that to the clipboard. So now I'm going to use those coordinates in a new tool called Upslope. So I'm going to come here and search for Upslope. It's a Saga tool. And so my target is going to be my filled DEM. My X coordinate, I just got those coordinates from the coordinate capture. So I can still read them. I could just type it in. But I captured them to the clipboard, so I'm going to select this and go Control V. And you see that it's copied everything. So I'm going to delete everything but what I want. All right, and so that's going to be my X value. And then I'm going to select and Control V, and we do the same thing, and I'm going to get rid of everything except this last number. And that should be my Y value. I think I've got these right. If you look, this Y coordinate is an order of magnitude larger, and that would make sense, right? We're quite a ways from the equator, but if this doesn't work, we'll come back and change this, okay? All right, so we will use, I'm going to go ahead and say that we're going to use the filled DEM here for this elevation. This target area, let's go ahead and that's optional. I think that's if we have just a sub area that we want to work at. So we're going to set elevation to filled. So make sure that you don't put anything up here. Sync roots we don't need. Method we're going to use D8, deterministic 8. The file that we're going to create, we need to give a name. So let's save to file, and let's call this Jackson Creek Shed. Let's see if that works. And so I think that's everything we need. So let's hit run and see if this worked. All right, let's go take a look. So if we go ahead and find JC Shed, and we're going to zoom to this layer, and you see it's the same size overall as our original DEM, but we've got two values. We've got 0 and we've got 100. And you can see that the channels show up on there. So let's turn those channels off. And so 0, the black, is everything that's outside of the Jackson Creek watershed, and 100 indicates what's inside. If we drag our Jackson Creek shapefile, okay, so here I've dragged that Jackson Creek shapefile so you can see where Jackson Creek is, and this doesn't look right, does it? Like, this watershed seems much too large. So let's go ahead and turn that off. And let's turn our channels back on. And you see what happened here. We chose our pour point on the Bayou du Chien, right where Jackson Creek runs in. And so it doesn't get just the Jackson Creek watershed, it gets the entire watershed. So that goes to show you that picking your pour point can be very important. And I messed it up. So let's go ahead and run it again. So again, I'm going to zoom in. And this time I'm going to choose my pour point just up a little bit on this Jackson Creek arm. And so again, just like I did before, I'm going to start capture down here, find my spot. I want to make sure that I'm on the raster as well. So there's a good spot right there. And so here are my coordinates. I'm going to copy them to the clipboard. And now I'm going to run the upslope area again. And so my X coordinate, I hit Control V. I get rid of everything except my X coordinate. My X coordinate is the smaller of the two UTM coordinates. Control V to paste those coordinates again. Get rid of everything except my Y coordinate. My elevation model is my filled DEM. My method is deterministic 8. The new raster I'm going to create, I want to save. And I called that, so I'm going to call this Jackson Creek Shed 2 this time. And let's let it run. All right, let's check this one out now. So if I zoom to that layer, now that looks a little bit better, doesn't it? And so if we consider the Jackson Creek area, you can see that now we have delineated just the watershed around Jackson Creek. And so that is awesome. That's exactly what we want. Okay, so now we have the Jackson Creek watershed in raster form, and we might use that in the future, but it also might be nice if this was in the vector form, if we had this as a polygon. So we're going to come up here to raster, conversion, and polygonize. Turn it into a polygon. So our input later is this JC Shed 2. This is the new one we made. And we don't really need to worry about the name of the field to create, or you can change that name. Doesn't matter. And so we want to go ahead and give it a name for the shape file. And so we're going to call this JC Shed Poly. And let's hit run. And so now let's go ahead and zoom to this new polygon. And again, that raster was the size of our original DEM. We just want this one small sub area. But it did that because it coded 1 for inside the watershed and 0 for outside. Let's illustrate what we're looking at by changing the symbology here. And so we're going to categorize it based on the one file it has. And we classify. We can hit OK. And so again, you can see that our polygon has two shapes, outside the watershed and inside the watershed. Let's get rid of all this outside. If we look at the attribute table, okay, and so if we take the select tool and select this polygon, and we come back and look at the attribute table, you can see that, again, 0 indicates outside the watershed. We don't want that. And this 0 is just no data, and we don't want that either. Let's get rid of these two things. Well, we're right here. We can edit right here in the attribute table. We can just turn on editing, and we can select this and trash it. And we can select this and trash it. And we're left with just the one polygon that we need. And so let's stop editing, save our edits. And now if we go and change the symbology, we still got those other values in here. Let's get rid of all of them. And let's just go ahead and classify again. And, well, it's still going to give us two values, but only one shows up. And so if I turn off that raster, now you can see the Jackson Creek watershed as it relates to the rest of the Watershed. And so there you go. So now you saw how you could make smaller sub-watersheds as well. Okay, well, there's a lot more we can do, but I'm just going to show you one more thing so we can wrap this up. So one simple question we'd like to answer is, what is the size of the Jackson Creek watershed? And we've got a polygon, and so let's just figure out the size of this polygon. So there are, again, many ways to do this. Here's one. I want to come up here to Vector, Geometry Tools, Add Geometry Attributes. And so this watershed polygon that I want is the fixed JC Shed Poly. And I'm going to calculate using the layer coordinate system or the project. They're both the same. So I'm going to calculate it using UTMs. So my answer should be in square meters. And I'm going to create a new file that's got that information in it. So I'm going to go ahead and save that. And this is going to be JC Shed Area. And so it's going to create a new shapefile, but this shapefile will have the area in it. So that sounds good. So let's run it. If I close, so again, I've got another polygon here. But let's look at the attribute table for this polygon. So right click, open attribute table. And look, I've got not just the area, but the perimeter. And so this is the area in square meters. And this is the perimeter of the watershed in meters. Pretty slick, so that's good to know. Now, it would be nice to know the area of the entire Watershed watershed, because that is just good information. And so let's zoom. Okay, so remember way back when we created this basins file, that includes all the basins, including this big one, which is Watershed. Let's turn off our Jackson Creek ones. Turn off our Jackson Creek shapefile. Okay, so this big area is pretty much the watershed of Watershed. So what is its area? Well, if we look at the basins attribute table, there's really nothing there, right? There's really nothing that tells us the area. But we can add it. And so let's go ahead and go over here to Open Field Calculator. And we're going to create a new field. So we're going to create a new column in this table. And we're going to call it area. Now we don't want it to be an integer. We want it to be a real number so we can have decimals. And so we're going to create a function down here that's going to fill in the value for every attribute in this table. And so we've got a whole bunch of things we could pick from, but we're going to code down here and pick from geometry. And you see $area. We went the one with the $sign. So I'm going to double click that and hit OK. And so now you have the area of every one of those polygons. And since we know that this is in UTMs, we know this is in square meters. And so which one of these is Watershed? Well, let's just take our select tool, select the Watershed area, and we can come down here and go to show selected features, and there you go. And so here is the area of Watershed in square meters. How awesome is that? All right, now typically when we talk about area, we don't want square meters, we want something like hectares. And so let's figure out this area in hectares. Again, many ways we could do this. Here's one. We're going to go back to the field calculator. We're going to create a new field. We're going to name this new field area underscore HA for hectares. We want a real number. And we're going to build an expression, but we're going to build an expression based upon that field we just created. Because we know we can convert square meters to hectares pretty easily. So I'm going to, in my expression, I'm going to come down here to fields and values. And here's that field we just created. So let's double click it. So that's in square meters. To convert square meters to hectares, we just need to multiply. So there's your asterisk and a space, or not a space. And we're going to go 0.0001. And so if you take the area in square meters and multiply it by 0.0001, that will convert it to hectares. And so let's hit OK. And now we have the area of Biodeschênes watershed in hectares. And not just that one, but if I show all features, oh, because I had that one selected, it only did it on that one. What do you know? Learn something. That's the only one I care about anyway. Hey, guess what? That's everything we're going to do today. So let me know if you got any questions, and have fun. See ya.